Good morning, everybody. We've got about another 5 minutes to go before we start the webinar. We're just waiting now for more people to join, and then we'll start at 10 o'clock UK time. Good morning, everybody. We've just got a couple of seconds to go. Just leave to see if a few more people join, and then we'll start at 10 o'clock exactly. Okay. Right, good morning everybody. The webinar today is mitigating fires and explosions from electrostatic discharges. My name is Mike Weaver, Associate Director of Sigma-HSE. What are the webinar objectives? Well, on completion of the webinar, you will learn how static discharges can be generated and accumulated in a facility, the different types of electrostatic discharges and their relevance, and ways to control electrostatic charge generation, accumulation, and more importantly, ignition in order to reduce the risk. A little bit about Sigma-HSE. We have technical offices in Winchester here in the UK where I'm based. This is our head office. We have units in New Delhi in India, Mumbai in India, Hyderabad in India, and New Brunswick in the USA. Our testing laboratories are based in Winchester, where we have a process safety lab, and a new lab we've built in Hyderabad in India. Our areas of expertise, well, we bring together our Indian in UK, well, our Indian American in UK experts to provide our clients with EHS services and appropriate engineering solutions. We undertake laboratory testing in our UK laboratories, and we test to ISO, BSI, and ASTM standards. So we basically cover the world for the different standards that are available. Our areas are consultancy, testing, and training. Our consultancy services consist of areas such as process safety management, implementation and review, DSEAR and ATEX assessments. DSEAR is only applicable in the UK. It's the Dangerous Substances, Explosive Atmospheres regulations. The rest of the Europe works with ATEX, which is Atmosphere Explosive. And the other thing I will add there is you've got another directive, the Chemical Agents Directive, which complements the two ATEX directives. We also deal with HAZOP, process hazard analysis, or PHA as you know it, functional safety such as SIL, chemical reaction hazards, and training workshops. Laboratory testing, we have powder, fire and explosion properties, gas and vapor properties, electrostatic properties, all of which can be carried out in both our Indian and UK laboratories. Along with these, in our UK laboratories, we have a fully kitted out chemical reaction hazards testing laboratory. So, why electrostatics? One of the 13 potential ignition sources given in EN 1127. It's specifically mentioned to look at when you're looking at ATEX compliance and DSEAR compliance. It's not very well understood and often is confused with standard electrical problems. It's too complicated. People regard it as a dark art, often blamed as an ignition source if they can't find anything else that's caused the problem. In most processes, it's ever present. and is inherent in the majority of processes. And it has caused a number of industrial incidents. One here in 2007, Barton solvents explosion. This is in a flammable liquid storage tank, and the static discharge ignited ethyl acetate vapors. The complete tank farm was destroyed. Nearby communities were evacuated. The reason for this is there was a float switch, a metal float switch, inside one of the tanks. And although everything had been earthed quite well around the plant, people failed to realize that the float switch was on a hinge, and the hinge was of make and break contact with earth. This caused sparking within the unit, and then the ethyl acetate vapor ignited. Again, people were doing the right things, but not checking every part of the plant to make sure you had what's called earth continuity. ExxonMobil explosion, February 2015. Electrostatic precipitator explosion. Well, in a precipitator, you will get electrostatic sparks occurring, but the hydrocarbon entered the unit and exploded because of the continuous sparks availability within the precipitator. On-site property damage and reported injuries to operator. So in this case, you were working with a piece of equipment that was designed to produce electrostatic sparks, but they failed to stop the hydrocarbon entering that hazardous area. Caswell Adhesives Fire 2007, adhesive factory fire due to static. Ignition of flammable vapors due to a static discharge. Fire destroyed the building. More than 60 firefighters were required to tackle the flames. 35 firefighters and 2 people were treated in hospital after breathing chemical fumes and smokes. One of the problems with adhesive factories are the fact that things stick to your feet, and the adhesive itself is often insulating, which means it coats things and ends up producing isolated conductors. So this is one of the problems when you're dealing with it, that you have to make sure that even then you've got systems in place, they are not compromised. To understand more about electrostatics, there's a couple of published guidelines. There's BSEN 60079-32-1 from 2015. This says explosive atmospheres, electrostatic hazards guideline. This will be used within Europe and a lot of other areas of the world to get an understanding and to follow the guidelines to make sure you're safe. In America, NFPA 77-2014 recommended practice on static electricity. Here's a slide here showing ignition sources by type of equipment. And green is the static, blue is the mechanical, and the grey color is smoldering materials. And as you can see, when you look at mixers, you have a large problem here with electrostatic discharges. The same with conveying, and then you get other effects in sieves, etc. The common denominator here is movement. There are a lot of moving parts, and the actual material is moved around quite dramatically at times, especially in mixers. And this is the places, again, where you will get high areas of electrostatic charge accumulation. So understanding static electricity, As I said, remember, static electricity is generated wherever movement takes place. And you get a shock. Why? Let's have a look at it and see where we're going. Well, what is static electricity? It's defined as an imbalance, a surplus or deficit of electric charge within or on the surface of a material. The phenomenon of static electricity requires a separation of the positive and negative charges. Static electricity is the same as mains electricity. It obeys very similar rules, but static electricity is generated in a much different way. Mains electricity is a constant voltage system. In other words, in America, you work on 110 volts. Within Europe, you work at 240 volts. But static electricity is a constant current system. So the current will stay constant and the voltage will rise or fall. Static electricity is not all bad. You can use it in photocopier machines. You can use it in electrostatic for spraying, especially for things like powder coating. Got electrostatic precipitators to try and get rid of the charge on a unit. And then you have it in printers as well to make sure that the ink adheres and stays well. So it's not all bad. There are a lot of problems though, especially in manufacturing. Shocks and nuisance. I think we've all experienced shocks which have made us jump back. You've only got to get out of a car sometimes and go to close the door and you get an electrostatic charge. That's because the discharge occurs because you as a person have built up a charge and you're on insulating shoes. The car is on the other side with the other charge, and then that's dissipated through the tires. So there's a charge imbalance. You touch the door and you discharge to the door, not the car to you. Clinging powder attraction, big problem with electrostatics. As you know, things cling. You've only got to look at your jumper. It sticks you if you're not careful. This can also cause an industry powder attraction. It's actually used in powder coating techniques to coat and cling to pieces of metal, for instance, that they're spraying. It can also cause powder separation because objects charge at different rates. So you can see on the right, charge separation in the middle of the material at the bottom and at the top. This is not what you want, especially in the pharmaceutical industry, where you've only got small amounts of API there. You want them to stay mixed with the excipients. The worst case scenario, having an EX rated area, a zone 0, a zone 1 or 2, a zone 20, 21 or 22, and then you get an electrostatic spark occurring within it. This can be the worst case where explosions occur. An example, electrostatic discharge here, operated in the vessel, ignition, fire occurs. So what are the definitions when we're looking at electrostatics? If a material is conductive, then it has a low electrical resistance. Electrons flow easily across the surface or through the bulk of these materials. Copper is a good example of this, used in cable manufacture. Charges go to ground or to another conductive object that the material contacts or comes close to. They possess a conductivity greater than 10 to the 4 picosiemens per meter. Picosiemens per meter is a measurement of conductivity. Resistivity is the measure of the resistance of a material. 1 over R is the conductivity. Anti-static, static dissipative. Today, we drop the term anti-static and we talk about static dissipative materials. For these materials, the charges flow to ground more slowly and in a somewhat more controlled manner than with conductive materials. Charge generation rate is less than the charge relaxation rate. In other words, it reduces the charge faster than it grows. You tend to use static dissipative materials on floors, etc., gloves and shoes. If you had conductive materials, then you would get a charge going through someone very rapidly and they would probably get severely affected by it. Whereas the static dissipative discharges at a set rate. Non-conductive or insulating. These materials prevent or limit the flow of electrons across the surface or through their volume. And always remember, with plastics, for instance, who are insulating, you can dissipate the charge along the surface, they have surface resistivity, or through the material with volume resistivity. They have a high electrical resistance and are very difficult to ground. Static charges remain in place on these materials for a very long time. Charge generation rate is greater than the charge relaxation rate. For an insulating material, a powder I had in the past, we charged it, fully charged, in a stainless steel vessel which was earthed, and after 28 days it had lost no charge at all, which shows the dangers these can produce when manufacturing. And then we talk about static electric discharge. This is the release of the static electricity in the form of a spark, brush discharge, propagating brush discharge, cone, or corona that might be capable of causing ignition under appropriate circumstances. So you must be able to identify what type of spark you could get in your system and whether it become active, and more importantly, will it become effective? So we have to do a static hazard assessment. First thing we need to realize is, do we have a flammable atmosphere? If yes, then we put that in the middle. Can we get charge generation? In a majority of cases, the answer to that is probably yes. Charge generates wherever movement takes place. And in an industrial scenario, you have movement everywhere, from people walking to powder going down a tube to mixers, etc. So charge generation can occur. Can it accumulate? This is the next question. Can you generate charge and will it accumulate within the system? Do you know the material ignition sensitivity? How are you going to do a static hazard assessment unless you know how sensitive the material is to ignition? You may generate and accumulate charge, and the discharge may only be 3 millijoules. The MIE of the material is 100 millijoules. Therefore, that ignition source can't ignite the material. So knowing the type of discharge you can get is imperative as well. This goes all into the static hazard assessment that you would do. Flammable atmospheres, if you look at gases and vapors, then you can see in the picture here the zone 0, zone 1 and zone 2 areas where gases or vapors are present all the time under normal operation or just some of the time. You need to know its flash point. You need to know its limiting oxygen concentration sometimes. Liquid conductivity, can it hold charge or not? The gas group of it, using the maximum experimental safe gap or minimum igniting current equipment to find the gas group. The minimum ignition energy, how much energy is needed to ignite it, often with gases and vapors less than 1 millijoule. The flammable concentration, the LEL and UEL, and are you working within that flammable concentration? And the vapor density, does it rise? Does it fall? Where's the biggest hazard you've got? In the roof or along the floor? The same applies for dusts. You look here, zone 20 this time, 21 and 22, the same definitions all the time through normal operation and infrequently. And for this, we talked about the minimum ignition energy, important when you're dealing with static. The minimum explosive concentration, there's no upper here, just the minimum. So are you above the minimum explosive concentration? Powder resistivity and charge relaxation time. Can it build up charge? Can it hold charge? Is it insulating, static dissipative, or conducting? If you're looking at nitrogen inerting, you may need the limiting oxygen concentration. And a good idea of the particle size. The smaller the particle size, the more dangerous the explosion, the easier it is to ignite it. So in our static hazard, we talked about charge generation. The most common charging mechanism is contact, or what we call tribocharging. This depends on the triboelectric series, from positive at one end down to negative on the other. At least one of the materials must be non-conducting, insulating, whether it's the pipe or the material itself. And if you look here, you've got someone pouring a bag of powder. Inside the bag, it becomes negative. On the floor, it becomes positive. You have liquid flowing through a tube. You get positive charge on the outside of the tube and negative on the inside of the tube. You have someone walking on an insulated floor with insulating shoes, and you get charge sharing here, where you get shoes charging to one polarity and the floor to the other. The same applies here. Things like polycarbonate sheets can generate huge amounts of charge, here on the roller and there on the sheet. Same with spraying. Again, movement here, pretty violent, and therefore you get charge on the gun and charge on the liquid. And the same here when you're filling a vessel and a mixer in here. The charges dissipate, the outside of the vessel becomes positively charged, inside negatively charged. Other mechanisms we can find are charge sharing, induction charging, which can only occur with conductors. So contact charging, here, liquid transfer through hoses and pipes, agitation of a two-phase mixture, settling of two-phase mixtures, filtration. All these are contact sharing of charge. You get the same with powder handling, in sieving, in pouring, mixing, milling, and pneumatic transfer. And on the right, you can see the pictures of things happening here. You've got a mill there, where again, you get large amounts of static being built up within the mill. Induction or ionic charging. A simple way to describe it here. You have two metal spheres mounted on insulating stands. The presence of a negative charge induces E to move from A to B. The two-sphere system is polarized. One of them is positive, one of them is negative as you're charging it. Then you separate sphere B from sphere A, pulling it with the insulating stand. Now the two spheres have opposing charges on them. Sphere B is negative, sphere A is positive. The excess charge distributes uniformly over the surface of the sphere. Bring an earth to it, and then it will discharge. So then you can get charge accumulation. Charge accumulates if charge generation exceeds charge decay or relaxation. This can occur in areas such as isolated metal plant, personnel wearing insulating shoes, for instance, non-conducting materials such as plastics, plastic sheets, polycarbonates, etc. It can happen in bulk liquids, where the liquid can charge up to a high level, and then it can discharge, and I've seen in instances here of penetrating glass vessels and puncturing them. I've also seen PTFE coated pipes looking though a machine gun had gone through them, going to earth from the liquid. Bulk powders are another one. FIBCs, silos, etc., where you have large bulks of powder. And then it can happen with mist or dust clouds. Both of these can accumulate charge. So charge accumulation. If you look for the conductors here, in A, we have a piece of pipe insulated away by the seals on the joins. That can build up large amounts of static, and then an earth comes close to it and it can discharge. If you look at the metal drum in B, sitting on a plastic sheet, it has no continuity to earth and no earth lead connected. C, this is where a conducting metal powder is inside a plastic insulating drum. Again, the wording continuity to earth occurs. The metal inside keeps its charge. When you go to pour it into a metal vessel, for instance, that's earthed, you will get sparking occur. Here on D, you see people walking, and again, you've got a conductor as the person sitting on insulating shoes, and as you know, you touch a doorknob, etc., and you get a discharge. And the last and final one there, you see the donut rings there, which are conducting, and the pipework is insulating, and again, you get this charge building up where it can discharge to earth and cause an issue. Insulators, we all know that insulators build up charge, and here's some examples: shrink wrap going around, insulating powder coming through a dust extract, dust filters. These may have polypropylene filters in them, which can build up static charge, and then we're dropping insulating powder into a metal vessel. So what type of electrostatic discharges do we have? Well, there's 6 types, not in order of energy, but the most common are spark discharges. These are the ones you commonly come up against, such as you touching the doorknob. Brush discharges, these are very low in energy, and these occur when you take a jumper off or something like that. Propagating brush discharges can be massive energies, up to a joule. Corona discharges, very low energy. You see them on spikes, for instance, in cone discharges that occur within silos, etc. And outside, you get the lightning type, clouds building up vast amounts of electrostatic charge and discharging to earth. You need to know effective available energy depends on the source of the discharge. To give you an idea of some, corona, sharp point of earth conductor near a highly charged object, minimal energy, non-incentive, unless they develop into a spark. Brush charge insulator, discharge to earth conductor, 3 to 4 millijoules. Gases and vapors can be ignited, but not dust. Not even if your MIE is 1 to 2 millijoules. Brush discharge has been proven not to ignite dust clouds. Spark discharge, the most common one. Human being, etc., isolated conductors, charged isolated conductor discharged to earth or another conductor. Half CV squared is the energy, and they can ignite gases, vapors, dust, or mists, where the energy is greater than the minimum ignition energy of the material. Cone discharge is highly charged insulating powder filled into metal earth silos. This is where granules build more charge than fine powder. So the worst scenario you have is insulating granules with a dust cloud above it, and they can ignite gases, vapors, dust, mists, where the energy again is greater than the MIE. Propagating brush, two surfaces of a high resistivity material oppositely charged, and basically they short circuit up to a joule, and they can ignite just about everything. So corona, usually with a sharp point of edge, highly charged conductor or insulator, energy very low, 0.1 millijoule, very sensitive gases, maybe groups C gases such as hydrogen, and can ignite gas in highly oxygenated mixtures. Brush discharges. If charges of one polarity are distributed on the surface of an insulator, brush discharges can occur as soon as the surface of an earth electrode nears the surface. Energy associated 3 to 4 millijoules. You'll see this when you're taking off a nylon jumper in the dark. You'll see those little sparks. They're brush discharges. Caused by, for example, things like insulating sacs. Brush discharges can occur from liquid surfaces of charged insulating liquids, from charged dust clouds, and from charged thunderclouds. Spark discharge, as I said, the most common, charged isolated conductors. They occur between earth and an isolated metal drum and trolley, for instance. There's nylon wheels on the trolley. So although you may have earthed, you may think the system carries on to earth, unless you actually put an earth lead on the metal trolley, you will have an isolated conductor. Isolated people there, insulating floors or footwear. Isolated pipe section. There's the joins insulating off that part of pipe which can discharge. Isolated conducting liquid in insulating plastic drum. So though the liquid is conducting, it can't discharge to earth because of the plastic drum. When you go to pour it, it can discharge. Cone discharges. These discharges are observed in connection with charged and highly insulating bulk solids when they're filled into silos and containers. They're called cone discharges because when you fill a silo, it goes into a cone. The picture shows the discharges going across like electrostatic hands of fingers of light running across the surface of the material. Cone discharges aren't usually observed in dust volumes below 1 meter cubed, though they can be seen in FIBCs. Luminous discharges may propagate along the surface of the powder heap. Up to 25 millijoules for fine powders, but much higher energies for granular powders. Insensitivity, vapors, gases, and sensitive dusts. One I looked at was an explosion where the explosion vents went off. in a silo where they produce in plastics for windows and doors, etc., in large granular form with fine dust above it. It was observed by a maintenance guy through an observation window that there was a fluorescent blue glow that he noticed with fingers of light across the top of the powder. And this is what resulted in the dust cloud explosion a couple of days later. Propagating brush discharges. This is high charging situations on high resistivity materials, insulator with metal close by. In other words, an insulator with a metal substrate on it. And thus can cause the discharges, the charge to build to significant levels, like an electrolytic capacitor, and then finally it will discharge. You can get this when pneumatic conveying with coated metal duct or pipeline, internally coated cyclone, insulating bulk container on earth's discharge chute, high-speed conveying belts. Couple of instances, tanker discharging plastic granules into a silo, smearing the bends on the pipe. And because of the smearing plastic on the pipe, you got the propagating brush discharge. This ignited the dust within the pipe and blew the tanker over. Another one was plastic polycarbonate sheeting cut off, put into a low very low storage container. An operator came there to push it down because it was at the weekend. And when he went to touch it, the brush discharge occurred, which put him in hospital for 6 days. And we have lightning type discharges. It's a massive electrostatic discharge between electrically charged regions within clouds or between a cloud and the Earth's surface. Occurs in the atmosphere with very large clouds, much bigger than industrial plant. So electrostatic hazards in plant. We need to consider these. Metal components. Isolated conducting fixed and mobile objects can store energy and be the source of spark discharges. This is where earthing is very important. And again, the term continuity to earth is imperative. So though you may put an earth on a pipe, you need to check that the earth is continuous down the length of the pipe right to the other end of the components. It could be insulated by joins, paint, and other such things. Energy can be up in the range of 100 to 500 millijoules, and energy can be compared directly to the worst case MIE for the materials. So if you've got a fairly low MIE, then having isolated conductors around is not a good idea, because this can produce discharges higher than the MIE of your material. Personnel. It's not just the hazard or the risk of ignition of dust clouds, they also can be annoyance. And they also can produce people doing body movements of shock, pulling back and putting themselves in danger of going into other equipment, etc. Basically, the human body is a conductor and can be a source of spark discharge. Charging by contact, such as walking, charging by sharing, touching, and induction, standing next door to something, can occur. Static shocks, 0.1 millijoules, undetectable by touch. Ignites hydrogen, carbon disulfide, and hydrocarbons and high levels of oxygen. 0.25 millijoules, still undetectable, but may ignite hydrocarbons or many gases in air. 1 millijoule, detectable, and ignites some sensitive dust clouds. 10 millijoule, you get a prickling sensation. This ignites dust clouds. 100 millijoules, slight muscular contraction, very incentive. 1 joule, 1 sharp muscular contractions occur, and I've understood that the guy with the polycarbonate sheeting, the whole of his arm went black all the way up. Potent incentivity, and not the sort of thing you want have happening on your plant. Charge generation of non-conducting materials. Tribocharging, contact and separation with other surfaces, discrete or continuous. Charge sharing, contact with other charged bodies or materials. Ionic charging, but no charging by induction. So typical charging systems for non-conductive solid materials have movement in materials in plastic pipes, for instance. Moving of plastics, highly insulating within metal pipes can happen. Emptying, filling sacks and bags. These generate electrostatic charge generation. Processing sheet or film. Again, very high levels of charge can occur here. Sitting or walking on insulating surfaces. Again, these can generate charge and pass it on to isolated conductors. Hazards from non-conductive solid materials. Can isolate conductors where you get a spark hazard, the person walking, for instance. Nozzles and lances, often put onto plastic pipes. These have often a wire grill going round them. These have to be earthed, otherwise the plastic isolates the nozzle or lance, and the spiral then is also isolated. It can discharge to earth and can create an ignition. So we spoke there about the wire helices going through these pipes. Again, they must be earthed both ends. You get gaskets isolating bottom bins, for instance. Again, if you're going to have this effect, then you need to make sure you get continuity of earth across the gasket. Flanges isolating ball valves, the same problem. You may have to use jump leads across them or to them to ensure that the ball valve is not isolated. And backing flanges, same problem again. You must take continuity of earth. They can lead to an ignition risk from brush discharges. These can ignite gases, vapors, but as I said before, not dusts. They can get propagating brush discharges, PBDs, and these can ignite gases, vapors, and all dusts. Powder charging. Charge is generated on powders during various operations, such as conveying, milling or grinding, sieving, pouring, filling, emptying of vessels, sacks, etc. It's good to have the volume resistivity and charge relaxation time of your materials, and that way you have an idea about whether you can generate and you can accumulate charge within your materials. What sort of risk are you running with your materials? Liquid charging, you get it during pumping, agitation, filtration, mist formation, all parts where movement takes place. And if you look at filtration, you have other properties coming there where you get a lot of agitation, you get a lot of charge buildup on there. Mist and dust clouds. These can happen, for instance, when spraying here. You can see the charge separating and moving from the material to the nozzle. The mist and aerosol and dust clouds can be highly charged. Even with conducting materials, they can build up static charge. Mist can ignite below their LEL. So the mist can ignite below the lower explosion limit of the liquid. The charge levels depend on how mist is generated, may induce charges on isolated conductors. So hazard summary. Establish that a flammable atmosphere or can be present. What is the ignition sensitivity of the flammable atmosphere, the minimum ignition energy? Again, how can you do a static assessment without having that value? And be careful that if your material gets finer and finer during your processes, as things improve and increase, get your material retested to make sure you are still covered. Do operational conditions affect the MIE? Temperature, pressure, low temperature, low pressure, high temperature, high pressure may affect the MIE. Insulating or conducting are the materials either that you're passing through, the materials of construction, or the properties of the materials going through. Are they insulating or conducting? Where will maximum charge occur within the system? Wherever movement takes place. So these are the first places to look. Mixers, blenders, that type of place. Estimate, measure the charge rate. Sometimes pretty difficult, but you'll get an idea how much charge is building depending on the way the operation of your system. What type of discharges are relevant? Can you get brush discharges? Can you get spark discharges? If you've got silos, short, dumpy, fat ones are the worst. Can you get cone discharges? And can you get propagating brush discharges? Can the maximum stored energy be calculated? Difficult again. Is action to prevent, reduce, and control electrostatic hazards necessary? 9 out of 10 times in an industrial plant, this is necessary. Prevent, reduce, or control the hazard. I went to one area where I said to someone they had a pipe, plastic pipe, going across a walkway to the equipment on the other side. And I said to him, do you know there's sparks occurring on the helix of the pipe? You need to earth it. So he thought he'd go one better. So he wrapped copper tape tightly round the plastic pipe and earthed it both ends. And then he ended up getting a propagating brush discharge, which blew up his equipment. Knowing what you're doing is imperative. So control measures, electrostatic hazards, bonding. Here we see the bonding with the lorry. Grounding, we see earthing the vessel and the lorry. Bonding and grounding. We've got both grounded, and the two are bonded together. Check to ensure no isolated conductors can occur. So avoid or minimize charge generation. Often difficult, but you can look at ways of doing it, changing over to metal transfer, for instance, making sure grounding of earth is in place, slowing down the way you fill a vessel. Prevent charge accumulation. Again, have earthing there that you can discharge the charge away. Remove charges before hazardous potentials are reached. If avoidance of static charging in incentive discharges cannot be prevented, then flammable atmospheres must be avoided or controlled. In other words, you'll probably end up using nitrogen inerting. Control of static Bonding or grounding. Bonding is the act of connecting objects together to ensure they are at the same voltage. Bonding distributes electrostatic charge equally between the bonded objects so that there is no risk of sparking between the objects. Grounding, connection to suitable earth point with a suitable electrical cable. Interesting to note that when you do your electrical maintenance on site, grounding and earth leads are not included in 9 times out of 10 that I visited plants. And even on a forklift truck charging point, gas charging point, I found earthing cables there, broken or not connected. They were of no use whatsoever. Also, finding on metal plant, on pipes, isolated conductors there where the earth had not been checked all the way through. Try to make it part of your maintenance schedules. Bonding does not remove the risk of static sparks entirely. If an object at a lower voltage, i.e. a grounded hose, comes into contact with equipment, this could result in a static spark discharge. So grounding and bonding together are probably the best way of dealing with it. But make sure grounding is there somewhere. Earthing requirements, metal to metal. Earthing resistance should be measured at less than 10 ohms for metal plant. This also complies with lightning requirements. So get your electricians to measure the resistance to earth along the complete length of pipework and any metal storage vessels or operating vessels, or floors, for instance, if you've got metal grills. Earthing requirements for pipelines, usually earth by connection to plant, flange bolts, vessels and structure. Bonding across joints are not necessary in many cases. Measure it. If it's acceptable, you don't need bonding across them. Exceptions may be found, for example, where you've got sleeve couplings or you've got very aggressive environments near the sea, for instance, where you may have a lot of salt, which creates corrosion. And also note, if painted pipework is in place, then use serrated washers to cut through the paint and ensure earth contact. Earthing requirements for movable equipment. Drums, trucks, feeders, drum pumps, movable plant in hazardous areas. Some pumps are put in, some small mixers are moved in. Make sure earth contact with a suitable floor, but beware of insulating skid, feet or wheels. If floor resistance is variable or uncertain, use a flying lead and an electrostatic approved clip. Lead is hardwired at one end and the connection is made before the operation starts. Connection is broken only after the operation is complete, and check you've got continuity to earth again. Here's an example of a grounding proving unit. Connect it to the tanker, push the button, and then it will tell you green that you're okay to go, red you haven't got an earth, in which case you need to check through to see what's happening. Grounding measures on a centrifuge. You see the braided hose here. That has to be connected to earth on both sides. You can see the earthing wires going between the vessel, the pipework, and the braided hose, etc. And make sure the framework there is all earthed, and check continuity to earth yet again. Personnel. Flying leads can be used to ground personnel, but are impractical for people who have to move a belt. These are often used in the electronics industry when you're sitting on a bench, but not much use when you're moving around in a factory. More common to use static dissipative flooring in shoes. This will also include overshoes. It's no good having static dissipative shoes and putting on insulating overshoes. Do not rely on manufacturer's information, but every now and again get a sample of shoes and the floor checked to ensure they are static dissipative. I've lost track of the number of floors I've measured, I've been told, have been static dissipative, and I've found them to be insulating. We've also tested shoes which have been meant to be static dissipative, and again, they're found to be insulating. So I advise you, if you are using this method, to make sure your floors and your shoes are checked and tested to be static dissipative. This is done by the total resistance between the body and ground should be less than 100 megaohms. So, controlling static hazards. The following control measures can reduce the electrostatic ignition hazards. Use electrically grounded conductive plan. Sorry. For personnel, use static dissipative shoes and floors and close overshoes. Increase the liquid conductivity, control the flow velocity, prevent free flowing, falling or splashing of liquids. Sorry, I apologize. use use full bore valves are also important to reduce turbulence. Sorry about my voice, I've got a frog in my throat. Control of electrostatic discharges. Based on the properties and test results, if the electrostatic charges on the powder particles is sufficient to cause discharges from the surface of the bulk powder, one or both of the following measures should be followed. Then install inert gas blanketing or installation of explosion protection. Avoidance of ignition source here is not an option. Types of FIBC and the hazards. Type A, polypropylene insulating. They can cause brush, cone, spark, propagating brush. Do not use in hazardous areas. Type B, have a breakdown voltage, still polypropylene, have a breakdown voltage of less than 4 kilovolts. Brush, cone, spark, use only for flammable powders. Assess cone discharges, types B, C, and D. These cannot be earthed. Type C, conducting, less than 10 to the 8th ohm from any point on bag surface, must be earthed in use. If you don't earth them, they become an isolated conductor and a danger. Type D, a static dissipative. Type D FIBCs work if earthed or not. And also look at the liners. Are they suitable for use? It's no good having a type D bag and putting an insulating liner inside it. Get the liners checked as well. So FIBC selection, MIE greater than 1,000, A, B, C, or D, explosive dust, B, C, or D, flammable gases and vapors, C or D. 1,000 down to 3 millijoules, greater than 3 millijoules, then it's non-explosive BCD, explosive BCD, gases and vapors, CD. And finally, less than 3 millijoules, you've got the selection of C or D for all types, explosive dust, flammable gases or vapors. So, summary of the electrostatic webinar. You need test data to understand if there is an electrostatic hazard. Test data can include MIE, MEC, resistivity, charge relaxation time. I didn't mention chargeability, but chargeability is measuring the rate of charge of a powder as it flows through an object. So you could use several charging mediums such as plastic, glass, stainless steel, and then put the powder through them and see which one charges the most. We had an active pharmaceutical ingredient that its highest rate of charge was actually through stainless steel. So don't think because it's got stainless steel there that you're safe. Minimum ignition energy, flash point, lower explosion limit conductivity for liquids. Explanation of electrostatics, examples of incidents and types of equipment where electrostatic incidents have occurred. We've looked at electrostatic hazard assessments, looked at charge generation and charge accumulation, types of electrostatic discharge, looking at electrostatic hazards on plant, grounding and earthing, and the use and selection of FIBCs. Well, I hope you found it useful, and if you've got any questions, then please get back to us, and we'll try and answer for them. Thank you very much for attending.